We will now look at how will a real world problem be given to us. In the previous problem that we solved, we were given the problem in a question format. Essentially, it was well written for us and asked very clearly that what is the scope of the problem, what do we need to find. However, in real world, the problem will not be as clearly defined to us, so we need to think like an analyst. Let's just look at possible scenario or a situation. We are hired as a consultant by a company producing two types of water bottles. The management of the company asks you a question which could be as broad as, can you help us optimize our production and increase our profits from the two types of water bottles that we manufacture? Now, there are no numbers right here. There is no specifications how the water bottles are built. The next step that means is that we should ask those questions. What we will do is we will think of some questions that we can ask the management, and they can then get us connected with the appropriate managers within the production plant or help us find those answers. Let's look at some questions. One of them could be, how are the bottles made? So this will be a very generic question which says, can you give us the process chart, the processing times at each individual point in the bottle manufacturing? What are the limitations for the process? For our model, it means constraints. Then these could be, example, minimum quantities that need to be produced, limits on raw material or limits on labor, limits on process line, meaning is there a machine that can only produce a certain amount, which could be a constraint. How would one estimate profit from each type of bottle? And what is the market demand? Can you sell as many as you can produce? Or is that also going to impose a limit on the model? Based on your questions, now you will be able to get some answers from the organization who just hired you. So let's say what you find is that you're told that the bottles have to pass through a manufacturing process which involves 3 steps. And 3 steps are performed at 3 different plants, plant 1, plant 2, and plant 3. And you're also told that the bottles are produced in lots of 100 each. So the next information that you get is that the amount of time per batch needed for 2 types of bottle, the steel one and the coated one, are given in this table. So what you see is, you see that steel type of bottle takes per lot 1 hour at plant 1, same is the case with coated one. At plant 2, the steel type takes 1 hour, however the coated one takes 2, and then at plant 3, it takes 2 hours for both of them. And then it is ready for shipping. You will also find out that the production hours week for each plant are that plant 1 has total of 35 hours per week, plant 2 has 38 hours per week, and plant 3 has 50 hours per week. So we are told that the company makes $350 per lot on steel bottles and $450 per lot on the coated bottles. Finally, the marketing department tells that the production must be maximized to its full potential. That is, they can sell as much as the manufacturing can produce. However, you must produce a minimum of 8 lots of steel bottles and a minimum of 9 lots of coated bottles. So we have all the information in a more well-defined form. Now we will formulate this problem so that we can apply the modeling technique, the LP technique. We are asked to increase the profit, and the profit depends on number of steel bottles and number of coated bottles. We will pick 2 decision variables, X and Y, where X represents the lot of steel bottles and Y represents the lot of coated bottles. And the objective function again in this case is that we should maximize the profit, and it is given that $350 per lot of steel bottle and $450 per lot of coated bottle. So our total profit function is the objective function z is equal to 350x plus 450y. We are also given the following constraint. For plant 1, it takes 1 hour for type X lot and 1 hour for type Y lot. So steel bottles and the coated bottles both take 1 hour each per lot. So 1 multiplied by X plus 1 multiplied by Y should be less than equal to 35 hours of the week. However, for plant 2, X takes 1 hour per lot. However, Y needs 2 hours per lot. So X plus 2Y should be less than or equal to 38 hours of the total available time. Similarly, for plant number 3, it takes 2 hours per lot of X and 2 hours per lot of Y, and the total time of plant 3 is 50 hours per week. So 2X plus 2Y should be less than equal to 50. These are based on the plant availability constraints or limitations. Now, we are also told that we have to produce greater than or equal to 8 lots of steel bottles and 9 lots of coated bottles. So these are constraints based on minimum production. The next step, we'll find a solution with the graphical method, and the method is still the same. For each of the constraints, we plot those lines after converting them into equalities. So our red line is constraint 1, x plus 2, x plus y is less than equal to 35, or the line is x plus y is equal to 35. Line number 2, constraint number 2 is blue, and it is drawn by x plus 2y is equal to 38. And line number 3 is 2x plus 2y is less than 50, and so on. What's the next step? We identify the direction because of the inequalities. So x plus y is less than equal to 35, that means the region on the lower side of the line. X plus 2y is less than 38, again that means this region. And then we have 2x plus 2y is less than 50, that means this region below the green line. And x should be greater than equal to 8, which means it's the region on the right side. And y should be greater than equal to 9, which should be the region on the above this yellow line. So our feasible region is shown with the orange area. One thing you want to notice is that the constraint 1 and 3 are redundant, because in this case they have the same coefficients but different right side values. However, in the feasible region area, the constraint 1 is completely overshadowed by constraint number 3. So in the next step, we will find point of intersection 1, which is intersection of blue line and the brown line, that is constraint number 2 and 4, by solving the linear equation 2 and 4. And similarly, point of intersection 2, which is between blue and green. So it will be constraint 2 and 3. If we solve these two system of linear equations, we will get the point of x and y at point 2. Similarly, point of intersection 3 coordinates, point of intersection 4 coordinates, and this table actually shows us x and y values at point 1, 2, 3, and 4, and the objective function values. So clearly our profit is maximum at point number 2, which is 12 lots of x and 13 lots of y per week. So let's revisit the key concepts that we have observed so far. We will now give a definition to linear programming. It is a modeling technique concerned with the allocation of scarce resources. These resources could be people, capital, or material in the optimal way subject to constraints on resources. And LP models are easy to formulate, simple to analyze and solve, and are one of the most widely used models in the area of operations research. So where will we use linear programming models? They will be useful whenever we have to solve an optimization problem which is linear in nature. We will talk about what does linear in nature means, where we want to maximize, for example, our profit, or minimize, for example, travel time on objective function. However, we must fulfill certain constraints within which we need to operate. And this is the mathematical form of LP model. You have a objective function which could be maximized or minimized. It is generally represented by z is equal to c1x1 plus c2x2 plus so on. Or restrictions in the system which are constraints for us are represented in this form. For example, a11x1 plus a12x2 plus so on is greater than or less than equal to b1. And we have to be following a non-negativity restriction, which means x1, x2 and xn all have to be greater than equal to 0. Next, we find a feasible region, and then we identify the maximum or minimum objective function value. So these are the definitions of the variables that we've listed in the previous slide. Xj is the decision variable, what we want to find. Cj is maximizing or minimizing metric, which is the profit or loss. Aij is the magnitude of each variable or the amount that we use. Bi is constrained resource available, how much of it do we have. And I mentioned about, in order for us to use linear programming, we have to make sure that the functions are linear. For example, if we look in this table, for this equation, the relationship is linear between the variables x1, x2, x3, in this case as well, so we can apply LP technique. However, in this case, the relationship between x1 and x2 is not linear, and hence we cannot use LP. Same is the case here, where x1 is raised to the power of 2, and hence it is not possible for us to use LP technique for this kind of a system. So far, our LP problems had only 2 variables. How about if we have 3 variables? In that case, what we will have to do is the graphical solution will have to be solved using the x, y, and z coordinates. You can already see that the solution will be complex, and here is the difference between the 2 variable and the 3 variable. In 2 variable, the constraints are lines plotted on an xy plane, and in 3 variable, the constraints are planes plotted in x, y, z coordinates. And in 2 variables, the corner points are intersection of lines, and in 3 variables, the corner points are intersection of planes. Of course, as the number of variables go on increasing from 3 to 4, the graphical method starts getting more and more complex, and we have to find a different method of solving LP. We will take a look at that in the following lectures. A quick slide on terminology. These are some of the terms that we either have come across or will come across, and I will point you back to this slide once I'm introducing those terms. So we have infeasible solution, we have infinite number of solutions. We did see infinite number of solutions in the previous slides. Unbounded solution, optimal solution, binding and non-binding constraints, restricted and unrestricted, redundant constraints. We did look at redundant constraints as well.